Moisture, Clouds, and Precipitation, a lesson covered by Nicholas Cooper. So before we get into the actual lesson, I'll go over some key terms you may need to know for the lesson, and then later on I'll go more in depth and explain to you what they really mean and what purpose they serve. The first one is water vapor. Water vapor is an odorless, colorless gas that changes from one state of matter to another, such as solid, liquid, or gas, at the temperatures and pressures experienced near Earth's surface. The processes involved are evaporation, condensation, melting, freezing, sublimation, and deposition. During each change, latent heat is either absorbed or released. Humidity is a general term to describe the amount of water vapor in the air. The method used to express humidity quantitatively include mixing ratio, the mass of water vapor in a unit of air compared to the remaining mass of dry air. Number 2, vapor pressure, that part of the total atmospheric pressure to its water vapor content. Number 3, relative humidity, the ratio of the air's actual water vapor content compared with the amount of water vapor required for saturation at the temperature. And number 4, dew point, that temperature to which a parcel of air would need to be cooled to reach saturation. Adiabatic temperature changes. The cooling of air as it rises and expands owing to successively lower air pressure is a basic cloud forming process. Temperature changes in the air brought about by compressing or expanding the air are called adiabatic temperature changes. Unsaturated air warms by compression and cools by expansion at the rather constant rate of 10 degrees Celsius per 1,000 meters of altitude change, a figure called the dry adiabatic rate. If air rises high enough, it will cool sufficiently to cause condensation and form a cloud. From this point on, air that continues to rise will cool at the wet adiabatic rate, which varies from 5 degrees Celsius to 9 degrees Celsius per 1,000 meters of ascent. The difference in the wet and dry adiabatic rates is caused by the condensing water vapor releasing latent heat, thereby reducing the rate at which the air cools. The different ways to initiate wind movement are 1. Orographic lifting, which occurs when elevated terrains, such as mountains, act as barriers to the flow of air. Number 2. Frontal wedging, when cool air acts as a barrier over which warmer, less dense air rises. Number 3. Convergence, which happens when air flows together and a general upward movement of air occurs. Number 4. Localized convective lifting, which occurs when unequal surface heating causes pockets of air to rise because of their buoyancy. Air stability. The stability of air is determined by examining the temperature of the atmosphere at various altitudes. Air is said to be unstable when the environmental lapse rate is greater than the dry adiabatic rate. Stated differently, a column of air is unstable when the air near the bottom is significantly warmer than the air aloft. For condensation to occur, air must be saturated. Saturation takes place either when the air is cooled to its dew point, which most commonly happens, or when water vapor is added to the air. There must also be a surface on which the water vapor can condense. In cloud and fog formation, tiny particles called condensation nuclei serve this purpose. Clouds. Clouds are classified on the basis of their appearance and height. The 3 basic forms are cirrus, cumulus, and stratus. For precipitation to form, millions of cloud droplets must somehow join together into large drops. 2 mechanisms for the formation of the precipitation have been proposed. The first one is that in clouds where the temperature are below freezing, ice crystals form and fall as snowflakes. At lower altitudes, the snowflakes melt and become raindrops before they reach the ground. The second is that large droplets form in warm clouds that contain large hygroscopic nuclei, such as salt particles. As these big droplets descend, they collide and join with smaller water droplets. After many collisions, the droplets are large enough to fall into the ground as rain. So now that you know a little bit more key terms, now we can go more into the lesson. I'll start off with going over the different states of water. The first one is melting, which is water going from a solid to a liquid. Many people wonder, what is the melting point of water? Well, the melting point of water is not always the same as the freezing point of water. Here's a look at the melting point of water and why it changes. The melting point of water is the temperature at which it changes from a solid ice into liquid water. The solid and liquid phase of water are in equilibrium at this temperature. The melting point depends on a slightly pressure, so there is not a single temperature that can be considered to be the melting point of water. However, for practical purposes, the melting point of pure water ice at 1 atmosphere of pressure is very nearly 0 degrees Celsius, which is 32 degrees Fahrenheit. The melting point and the freezing point of water ideally are the same, especially if there are gas bubbles in the water. But if the water is free of nucleating points, water can supercool all the way down to negative 42 degrees Celsius, or also known as negative 43 degrees Fahrenheit, before freezing. So in some cases, the melting point of water is considerably higher than its freezing point. Next is evaporation, which is water going from a liquid to a gas. Evaporation of a substance such as water occurs when the molecules in a liquid state absorb enough heat energy to vaporize into a gas. The heat energy which causes the molecules to move is called kinetic energy. Next is sublimation, which is water going from a solid state straight into a gas state. Examples of ice to water vapor, which turns directly to water vapor without first transitioning into a liquid, is referred to as sublimation. In fact, any solid that turns into a vapor without going through the liquid phase can be said to sublime or sublimate. An example of this is dry ice. Next, we have freezing, which is water going from a liquid to a solid, and this occurs when the absence of heat causes water to expand and solidify. Next is condensation, which is water going from a gas to a liquid. Condensation generally occurs in the atmosphere when warm air rises, cools, and loses its capacity to hold water vapor. As a result, excess water vapor condenses to form cloud droplets. Next is deposition, which is water transforming from a gas to a solid. One example of deposition is a process by which, in subfreezing air, water vapor changes directly to ice without first becoming a liquid. Next, we'll talk about latent heat. With each phase change, a specific amount of latent heat is released or absorbed. Note that melting and freezing have the same value except that latent heat is flowing in an opposite direction. The same is true for the pairs of evaporation and condensation, as well as sublimation and deposition. Also note that the addition of melting and evaporation is a value of sublimation, as well as the addition of freezing and condensation is a value of deposition. Note that the magnitude of melting and freezing are much less than the other latent heat processes. Thus, melting and freezing do not contribute to cooling and warming the air as much as the other processes. For example, 7.5 times as much cooling occurs from evaporation than it does from melting. These processes contribute to cooling and warming the air and the troposphere. Below is an example for each. Melting, snow melting in the air as it falls helps cool the air. And evaporation, rain evaporating into the air and from the ground when and after it falls helps cool the air. Sublimation, surface snow vaporizing from the ground while temperature is still below freezing helps cool the air. And freezing, liquid cloud droplets being lifted into a very cold subfreezing layer in which they freeze helps warm the air. Condensation, liquid clouds developing as an air rising by positive buoyancy helps warm the air. And deposition, frost developing on the ground when temperature is below freezing helps warm the air. Note, warming the air does not always mean an actual increase in temperature, but could be a reduction in the amount of cooling. In other words, the latent heat warming is partially offsetting some of the cooling that would take place by another process. And as you see on the screen, you can see that melting absorbs latent heat, evaporation absorbs latent heat, sublimation absorbs latent heat, and freezing, condensation, and deposition help release latent heat. The next concept we will cover is humidity and relative humidity. What is relative humidity? Relative humidity is a measure of the amount of moisture in the air relative to the total amount of moisture the air can hold. For instance, if the relative humidity is 50%, then the air is only half saturated with moisture. Also know that warmer air can hold more moisture than colder air. Why is relative humidity important? Well, first off, relative humidity helps make clouds, precipitation, and fog possible. Without humidity, there would be no clouds, no precipitation, or fog. Humidity is simply water vapor in the air, which is needed to form rain. Additionally, water vapor holds heat in the air. It is a greenhouse gas, which means it is a gas that absorbs heat and warms the atmosphere. This is why humid air feels warmer. Relative humidity is reported as a percentage of the total amount of moisture that can be held in the air. For instance, if the air is only half saturated with water vapor, the relative humidity will be reported 50%. If the air holds all the water vapor it can hold, it is 100% saturated. A capacitance type sensor is commonly used to measure relative humidity. Changes in relative humidity cause the shape of the sensor to change. When the sensors change shape, its capacitance or ability to store an electrical charge changes in a detectable and repeatable fashion. Relative humidity is influenced by temperature and geographic location. Warmer air holds more moisture than cooler air, and warmer weather promotes evaporation. Areas with a lot of surface water, such as coastal areas and the Great Lakes region, have high humidity levels due to evaporation. Humidity is especially high in warm tropical areas, such as South Florida. Our next topic we will go over is movements of air. Movement of air is caused by temperature or pressure differences and is experienced as wind. Where there are differences of pressure between two places, a pressure gradient exists, across which air moves, from the high pressure region to the low pressure region. This movement of air, however, does not follow the quickest straight line path. In fact, the air moving from high to low pressure follows a spiraling route, outwards from high pressure and inward toward low pressure. This is due to the rotation of the earth beneath the moving air, which causes an apparent deflection of the wind to the right in the northern hemisphere and to the left in the southern hemisphere. The deflection of air is caused by a Coriolis force. Consequently, air blows anti-clockwise around a low-pressure center, depression, and clockwise around a high-pressure center, anticyclone, in the northern hemisphere. This situation is reversed in the southern hemisphere. Wind caused by differences in temperature is known as convection or advection. In the atmosphere, convection and advection transfer heat energy from warmer regions to colder regions, either at the Earth's surface or higher up in the atmosphere. Small-scale air movements of this nature is observed during the formation of sea and land breezes, due to temperature differences between seawater and land. At a much larger scale, temperature differences across the Earth generate the development of the major wind belts. Such wind belts, to some degree, define the climate zones of the world. Air temperature is generally higher at ground level due to heating by the sun, and decreases with the increasing altitude. This vertical temperature difference causes and creates a significant uplift of air, since warmer air nearer the surface is lighter than colder air above it. This vertical uplift of air can generate clouds and rain. Sometimes air from warmer regions of the cloud collide with air from the colder regions. This air mass convergence occurs in the mid-latitudes, where the warm air is forced to rise above the colder air, generating fronts and depressions. Clouds are formed by air being forced to rise. Some clouds form when air at the surface of the Earth is forced to rise, and there are three processes that force air to rise. The first is a low pressure system. Wind moves in towards the center from all directions because air moves from high to low pressure. When the air meets in the center, there is nowhere else for the air to go but up. Next is sloping. Air is also forced to rise when it's traveling over land that is sloped upwards. The air cools as it rises, and eventually clouds will form. And finally, we have weather fronts, which is caused by air to rise when the lighter warm air flows over the heavier cold air. All of these wind patterns help create and form the many different types of clouds as shown on the screen. The next topic we will discuss is clouds. Clouds may be classified by form and by height. This was first discovered by Luke Howard, a British pharmacist, was the first to describe the cloud forms. Clouds are condensations of water and other particles in the atmosphere. Cloud shapes and the dynamics of the formation are accurate indicators of important atmospheric properties, including air stability, moisture content, and motion. Clouds are divided into families of high level, middle level, low level, and vertically developing clouds, and are classified again in accordance with their general shape. High level clouds include cirrus, cirrostratus, and cirrocumulus clouds that occur in altitudes between 16,000 and 45,000 feet. Middle level clouds include altostratus, altocumulus, and nimbostratus clouds that occur between 6,500 and 22,000 feet. Low-level clouds include stratus and stratocumulus clouds that occur between the surface and 6,500 feet. Vertically development clouds include cumulus and cumulonimbus clouds and range in the development from the surface to 45,000 feet. The heights of the bases of clouds used to designate cloud families can vary with altitude. At extreme northern or southern latitudes, high-altitude family clouds can be observed at much lower altitudes. In general, cloud shape is determined by the method of cooling to reach condensation and the forces of winds that can shear or tear the cloud. Cloud opacity, an example, whether it is light or dark, is a function of cloud thickness. Cirrus clouds occur at high level and are generally wispy and elongate in form. Vertically rising air is unstable and gives rise to cumulus cloud formation. Cumulus clouds are billowy. Stratus clouds are heavily layered and often appear in sheet-like formation. High clouds, cirrus, cirrostratus, and cirrocumulus, are composed of ice crystals and dust or pollution particles. The particles often serve as centers of crystallization or condensation nuclei. Cirrus clouds often produce Mayer's tails that are tail-like wisps of ice crystals. Cirrostratus clouds, because they are thin and the ice crystals act to both reflect and refract sunlight, are often associated with halos of ice crystals that appear to encircle the sun or moon. Cirrocumulus clouds often appear as patch-like thin clouds. Middle-level clouds, altostratus, altocumulus, and nimbostratus, are composed of water with some ice crystal formation near cloud tops. Both middle-level and low-level clouds may be composed of supercooled water, water that is below freezing, that has not yet crystallized around a condensation nuclei. Altostratus clouds often present a bluish layered appearance. Depending on thickness, altocumulus clouds often have white or gray layers that appear in washboard or wave-like formations. Atmospheric instability and convective air currents can result in the formation of altocumulus castellanius clouds. Another form of altocumulus cloud, a standing lenticular altocumulus cloud, is formed by turbulent updrafts of air uplifted by terrain barriers. An example, mountains and/or ridges. Although dynamic, the standing lenticular altocumulus cloud formation appears static or standing over the terrain feature leading to their formation. Nimbostratus clouds often appear as heavy, gray, moisture-laden clouds. Low-level clouds. Low-level stratus clouds are usually gray clouds associated with precipitation and fog. Stratocumulus clouds present their familiar cotton ball-like cumulus shapes and an elongate form. For our final concept, we will go over the formation and the different types of precipitation. When cloud particles become too heavy to remain suspended in the air, they fall to the earth as precipitation. Precipitation occurs in a variety of forms such as hail, rain, freezing rain, sleet, or snow. The first one is rain, which is a liquid precipitation. Rain develops when growing cloud droplets become too heavy to remain in the cloud and as a result fall toward the surface as rain. Rain can also begin as ice crystals that collect each other to form a large snowflake. As the falling snow passes through the freezing level into warmer air, the flakes melt and collapse into raindrops. The picture below shows heavy rain falling from a Texas thunderstorm. Next is hail, which is a form of ice precipitation. Hail is a large frozen raindrop produced by intense thunderstorms, where snow and rain can coexist and the central updraft. As the snowflakes fall, liquid water freezes onto them, forcing and forming ice pellets that will continue to grow as more and more droplets are accumulated. Upon reaching the bottom of the cloud, some of the ice pellets are carried by the updraft back up to the top of the storm. Next is freezing rain, which are supercooled droplets freezing on impact. Ice storms can be the most devastating of winter weather phenomena and are often the cause of automobile accidents, power outages, and personal injury. Ice storms result from the accumulation of freezing rain, which is rain that becomes supercooled and freezes upon impact with cold surfaces. Freezing rain is most commonly found in a narrow band on the cold side of the warm front, where surface temperatures are at just below freezing. Next is sleet, which is frozen raindrops that bounce on impact with the ground. Progressing further ahead of the warm front, surface temperatures continue to decrease and the freezing rain eventually changes over to sleet. Areas of sleet are located onto the colder side, typically north of the freezing rain band. Sleet is less prevalent than freezing rain and is defined as frozen raindrops that bounce on impact with the ground or other objects. The diagram below shows a typical temperature profile for sleet with a red line indicating the atmosphere's temperature at any given altitude. The vertical line in the center of the diagram is a freezing line. Temperatures on the left of this line are below freezing, while temperatures to the right are above freezing. Sleet is more difficult to forecast than freezing rain because it develops under more specialized atmospheric conditions and is very similar to freezing rain in that it causes surfaces to become very slick, but is different because it is easily visible. Lastly is snow, which is an aggregate of ice crystals. Progressing even further away from the warm front, surface temperatures continue to decrease and the sleet changes over to snow. Snowflakes are simply aggregates of ice crystals that collect to each other as they fall toward the surface. The diagram below shows a typical temperature profile for snow with a red line indicating the atmosphere's temperature at any given altitude. The vertical line in the center of the diagram is the freezing line. Temperatures to the left of the line are below freezing, while temperatures to the right are above freezing. Since the snowflakes do not pass through the layer of warm air enough to cause them to melt, they remain intact and reach the ground as snow. Thank you for viewing, and I hope you learned more and enjoyed the video about moisture, precipitation, and clouds.